guys, I just wanted to step in here and give you guys a little pre-lecture about some tricks that we can use to help us evaluate double integrals. We've hopefully had a chance to practice doing some double integrals already, but sometimes they're not quite as straightforward as you might hope. On the plus side, there are some tricks that we can use when we're evaluating double integrals that maybe we didn't have available to us when we were just evaluating a single integral back in first semester calculus. So I want to just take a few minutes to talk about really three different tricks that I think will be helpful to us when we're trying to solve and calculate double integrals. One of them is this idea of reversing the order of integration. Okay, so it might be that you have a problem where you don't know how to do the inside integral directly. Okay, so one suggestion for how to get around that is to try to reverse the order of integration and hope that the new problem that you get when you reverse the order of integration suddenly becomes much more doable. Okay, I have an example here on the board I want to do with you really quickly. So what you see here, I've got a double integral. I've got the x on the outside, and I'm going to remind you that I always like to indicate here what the variables are. So the x is on the outside, and then the y is on the inside. Okay, and there's nothing wrong with that expression the way it is, except that I don't know an antiderivative for 1 over the ln of y with respect to y. So doing the inside integral here is not, this is not a standard integral. It's not something you're going to find in your table of integrals. You're certainly not going to be able to do a simple, u substitution or anything like that to solve this double integral. So my suggestion, if you run into something like that, is to think about possibly reversing the order of the integration. That's my first little trick that I want to go over here. In order to successfully do that, we need to draw a picture of the domain of the integration, the region of integration. I like to draw the region by using the x and y axes, of course. I'm going to draw them lightly on the board. And then I'm going to go back and draw a much darker set of these four curves. So x equals 0, for example, that is actually the y-axis. Okay, so that's x equals 0. The upper limit is x equals the ln of 10. That's also just a vertical line. Okay, so we have those two vertical lines. Then I have y equals e to the x. So that, of course, is a graph something like that. It goes through this point right here, which is 0, 1. Okay, and of course, when I plug in 10 here, let's see, what's that going to give me? E to the ln of 10 is actually just 10. So this is the point ln of 10, comma 10. And y equals 10 would go right through that point here. Okay? So again, if you kind of remember that the x-axis was not one of the curves here, right, then it becomes pretty clear what the bounded region is. This is what we usually call R. That's what the region is that we're going to be integrating over. We need to draw that region so that we can reverse the order of integration correctly. Right? We can't just look at these four equations usually and just immediately, without a visual idea of what's going on, be able to successfully reverse the order of integration. So once I've drawn my region, now I can make an effort here to put, what will it be, the y on the outside and the x on the inside. So this is what we're going to try to do. Now you can see, if we look at the y-axis here, where does the region occupy space with respect to the y-axis? Well, it's not here, it's not here, it's not here. We first hit it right here at y equals 1. Remember, the outside limits of integration always have to be constant numbers. And now we're going to integrate, 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 integrate until we get up to y equals 10. Okay, so the outside limits would be y from 1 to 10. And then if I stand somewhere with a y value between 1 and 10, and I look in the x direction, let's say right here, notice that I start integrating right here at x equals 0. And I stop integrating when I hit this curve. This curve is the equation y equals e to the x. But remember, we have to actually solve that for x right now. And when I do that, it just gives me the ln of y. Okay, so notice how the limits of integration have changed. The function that you're integrating does not change. We're still integrating 1 over the ln of y, but I'm now going to do the x integration on the inside. And this is going to turn out to be much easier to do than to try to do it in the original order. Because look, when you integrate with respect to x, right, I leave the y on the outside now, that 1 over ln of y can be factored out. And you're simply integrating x from 0 to the ln of y dx and then dy. When you integrate dx, right, you're just going to get x, which you will evaluate from the upper limit down to the lower limit. You're just going to actually get, this is so simple what happens here. This just becomes 1 over the ln of y. And this integral, the integral of dx, evaluated from 0 to ln of y, is just ln of y. And the beauty of that is now you can cancel the logarithms there. And now you're simply going to integrate dy from 1 to 10. And of course the answer there is 10 minus 1, which is 9. Isn't that great? An impossible integral to do in this order, where you would have to find an antiderivative for 1 over the ln of y, right, becomes so much easier when you reverse the order of integration. So this is a trick to keep in mind. It can be very, very useful to us when we're doing double integrals. Okay, as usual, you can always pause and stop and rewind if you need to. I'm going to erase this for now so that I can move on to a couple of other tricks to help us with double integrals. The next one is what I'm going to call symmetry. Sometimes we can take advantage of the nature of the region relative to the x and y variables and be able to just look at a problem and say what the answer is going to be. Now, before I actually get into how the symmetry plays a part, I want to make a quick remark here, and then I'll erase it and do an example. So this remark is really useful. So here's what it says. The interpretation of this double integral, so whenever we look at this double integral f of x, y, dA over a region R, when we first introduced this, we were interpreting that double integral as a volume. But it turns out that if our function, f of x, y, is negative, even if it's only partially negative for part of the time on the region R, maybe it's sometimes positive, sometimes negative, right? Then if that happens, if our function goes below the xy plane, right, if z is negative, then this interpretation breaks down. Okay, it's the same thing as if I give you back in Calc 1, right, if I give you a function that's down here, right, if f of x is down here, then of course the integral of f of x dx would be a negative number. But this region right here, right, definitely has a positive area. So it would be unfair for me to say, well, the integral is telling me the area, because area has to be positive. You can't talk about a negative area, but you can have a negative integral. Or maybe it's something like this. What if your function looks like this, right? Looks just like that. Now, if you do this integral, the integral is just going to cancel out to 0 because you're going to get a negative contribution here up until the graph crosses the x-axis. It's going to be negative. but then it's going to cancel out on the right-hand side where it's positive, and basically these two areas, they are the same, right? But the integral counts this one as negative and this one as positive and reports a net total of 0, even though the actual shaded area, again, has to be a positive number. So just be a little bit careful. The interpretation of an integral as a physical quantity, such as area or volume, is valid as long as your function, either f of x or f of xy, depending on what context you're looking at, as long as that function is greater than 0. Okay? With that in mind, I want to talk about symmetry. Okay, so I'm going to erase this. Symmetry, what is that referring to? Well, the idea is that if I just ask you to evaluate an integral, so here's an example of how symmetry could be used. Evaluate, let's say, a double integral over a region R of x dA, right, where R is bounded by, if R is bounded by, let's say, y equals 1 plus x squared and y equals 2x squared. Let's try to evaluate this. So I'm going to draw a picture of the region first. We're going to see how the symmetry plays a role here in just a second. I'm going to draw a picture. Okay, so here's my xy axes. The parabola 1 plus x squared, that's going to be, basically just your standard parabola shifted 1 unit upward. Okay, and then y equals 2x squared, that is a steeper parabola that also goes upward, but it goes through 0, 0. And you can see that your bounded region, your region R, is right in here. Okay? The place where these graphs cross, right, we can figure that out, where these points are. This is going to be the point 1, comma 2. And this is going to be the point negative 1, comma 2. So, for example, I could evaluate this double integral by setting up my limits. Okay, so I could integrate, for example, x from negative 1 to 1. And then I could integrate y. So in other words, here's x equals negative 1, and here's x equals 1. And then I can, for any such x between negative 1 and 1, I can look in the y direction. On the inside, I can integrate y from the parabola 2x squared, that's the one that's underneath, up to the parabola 1 plus x squared, which is up on top. Right? And then I'm integrating x dy dx. Okay? So that would be the setup of this integral. Okay, if you work this out by starting with the inside integral, so if I integrate the x with respect to y here, of course, I'm just going to get 1 plus x squared and then minus 2x squared. I can simplify that, right? This is going to be the integral of x from negative 1 to 1. Of x, and this is, if I just subtract this, this is negative x squared. So this would be minus x cubed. Okay, so now I have a pretty easy integral to do here. And if you actually do this integral, 1/2 x squared minus 1/4 x to the 4th, right? If you actually evaluate this integral from the upper limit to the lower limit, you are actually going to get 0. But my point is not all of this work. My point is that I already knew that the answer was going to be 0. Right? How come? Well, look at the region. And look at the function that you're integrating. X. Would you agree that on the right half of this shaded region, x is positive? So you're doing you're integrating the function x, a double integral, over a positive domain. But then on top of that, you're also integrating x on the left half, and on the left side of that region, x is negative. It's just like this picture here, right, that I was showing you before. The function is positive half the time negative half the time, and in exactly a balanced way is going to cancel out. This double integral is not telling us the volume underneath this surface anymore, because this surface, this function, is negative. It's below the xy plane for part of this region. Now, if my region was over here somewhere, where x is always positive, then yes, the double integral would tell me the volume underneath that surface and above this domain. But if my domain, if my region R cuts into a part of the plane where the function is negative, then I'm not surprised at all to get an answer that's not a volume, right? 0 is not the volume of anything. But it is what the double integral reports as the answer. The double integral is going to report 0 because of the symmetry. Okay, we're going to use the symmetry a lot, so this is a very nice trick. It depends on the shape of the region as well as the function. Now, if the function had been x squared, all right, well now x squared is always positive, even on the left side of this region. I won't be able to cancel anything out anymore. So if I was doing this double integral, I would have to go through all of these steps to get the answer. Okay, so the use of symmetry is a little tricky. It depends on the shape of the region and the function relative to that region. Similarly, if this had just been a y instead of an x, I also would not be able to use symmetry on this one because, you know, here is y equals 0 right here. The whole entire region is in the positive y portion of the plane. So there's no cancellation, canceling it out to 0 like there is for the x integral. So I'm not saying that just because of this region, all of my integrals are 0. Only the ones where this function, which was x originally, only those where this function cancels out its value on part of the region with the other part of the region. Okay, that's the idea behind symmetry, and we're going to have to practice it a lot to kind of get good at it. But that's my second trick for evaluating double integrals. I have one more trick, and it's to change the coordinate system. In particular, the only other coordinate system that we know for sort of the xy plane is polar coordinates. So, as an example, let me show you a problem where you wouldn't really want to do it using the usual xy coordinates. Suppose I ask you to do this problem here. Evaluate, so here's an example. Evaluate the double integral over a region R of y squared dA, where R is the unit disk centered at 0, 0. A disk of radius 1 centered at the origin. So the picture of the domain this time is just this whole entire disk right here. Now, that's very symmetrical. It looks like a nice symmetric region, but guys, this time, because the function is y squared, I really cannot set up a symmetry situation that's going to allow me to evaluate this very easily. I could maybe use symmetry to some extent, but I'm not going to get any cancellation. Y squared is always positive, right? So this isn't going to be equal to 0. I already know that. But for example, I could say that, you know, I could just integrate the first quadrant and then multiply the answer by 4. Because y squared, whatever the values of y squared are on the first quadrant, they will get repeated on the second, third, and fourth quadrant. Okay. So for example, we could actually do this one by sort of using, I'm going to use a little bit of symmetry. Okay, I'm going to take a factor of 4. X, so for this, just for this first quadrant, x is going to go from 0 to 1. This is a circle of radius 1. And then y is going, so that's x. And then y is going to go from 0 up to the circle. Now the circle has an equation like that. And when I solve that for y, you see I'm getting kind of I'm getting a limit of integration that isn't so pretty. And when you integrate y squared, of course you're going to get y cubed over 3. And when you evaluate y cubed with this radical, you're going to be getting a pretty messy integral. This is messy, it's hard to evaluate, even when you are using a little bit of the idea of symmetry. You're saying that whatever the volume is above the first quadrant for this surface is going to be the same volume in each quadrant, and so therefore you can multiply by 4. That's a good thing to take advantage of, but even with that, we still have a messy integral. Turns out that we can change coordinate systems and get a lot faster answer. Let me explain how you do that. What you're going to do is, and I'm going to come back and just take the whole entire circle again. I'm not going to use the symmetry at all. Let's just take the whole circle. Okay, remember the polar coordinate system? So we have x equals r cosine of theta. Y is equal to r sine of theta. It turns out that in polar coordinates, I will show you this another time. I don't want to get into the details right this second. But it turns out that the dA in polar coordinates, so what I mean by using polar coordinates is that instead of integrating x and y, I'm going to integrate r and theta. But there's a little twist to it that you need to learn, which is that in polar coordinates, the little piece of area that is going to be created when you chop up the domain is not just dr d theta, it's actually r dr d theta. So that seemed maybe a little bit counterintuitive why there's this extra r here. I'm going to show you that. I'm going to explain that. It's just a little tiny bit of geometry is all it takes to kind of explain that point. But for now, I just want to use this. This is something worth learning. You're going to use it a whole lot in the rest of the class. But what it allows me to do is, instead of integrating in the xy world, I'm going to integrate in the r theta world. So y squared, for example, is just going to be r squared sine squared of theta. That's just y squared. And then the dA is just going to be r dr d theta. You don't have to put the theta on the outside, but usually that is what people will do for most problems. That works well. Now look at the theta variable. Remember that theta is the angle relative to the plus x axis. For this region, which is the whole entire circle, theta goes all the way around. It goes all the way from 0 to 2 pi. One full revolution around the circle. Now, if you prefer, remember we talked about this, you could only do the first quadrant. That would mean putting a factor of 4 to take advantage of the symmetry, and then it would mean only integrating to pi over 2 instead of 2 pi. Either way is fine. Let me just go ahead and not use the symmetry this time. I'll just put the 2 pi back. And then if I imagine stopping at one of these angles, let's say I work with this angle right here, so I'm taking theta like that, I can ask, well, what are the limits for r? Well, I'm starting at the origin, which is a distance of 0, a radius of 0, and I'm going all the way out to the edge of the circle, which is a radius of 1. These limits of integration are a whole lot nicer than something like that we had when we tried to set it up in the xy coordinates. So polar coordinates are going to be a great secret here. So then how am I going to finish this problem? Well, I just have to do this integral here. I just have to do this integral. It's just like the double integral in the x and y coordinates. I do the inside integral first, which is the r integral. So I'm going to pull the theta part outside, sine squared of theta. When I integrate the r, notice that this is the integral of r from 0 to 1 of r cubed, dr d theta. The antiderivative of r cubed is 1/4 r to the 4th. When I evaluate that from 0 to 1, I just get 1/4. So it's just 1/4 of the integral of theta from 0 to 2 pi of sine squared of theta. And the way that you do that integral, you may remember from your previous math class, is you use a trig identity to write that as 1 minus the cosine of 2 theta all over 2. That's just a trig identity. And then let me finish up here. If I pull the 2 out, I'm going to get a 1/8. I'm going to integrate, so now I'm just going to integrate this, right? I'm just going to get theta minus 1/2 of the sine of 2 theta. So I did a little u substitution there, nothing too crazy. And then I have to evaluate theta from 0 to 2 pi. The sine of any multiple of pi is just 0, so this part's going to go away. I'm just going to get 1/8 of 2 pi. In other words, my answer is just pi over 4. It's just pi over 4. So that is the answer. So there's an example showing how polar coordinates can be used. I have not explained this little dA expression here very thoroughly yet, but this is always what you're going to need to include when you choose to use this third trick over here, the polar coordinates trick. So 3 great tricks, guys. 3 great tricks for doing double integrals. Okay? Reverse the order of integration, use symmetry, and possibly use polar coordinates. I hope this helps make some things clear for you. We'll talk about it more in the future, but for now, that hopefully gets you started. Thanks a lot for watching. See you guys soon.